Talking about AI, don't you know? Neural networks and deep learning too. In this podcast, we'll break it down for you. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data science models, we can't get enough. This podcast rocks, it's never too tough. Got questions, we've got the scoop. Join our tech-savvy podcast group. From beginners to pros, come one, come all. Machine learning's fun, we're having a ball. Machine learning, oh what
Hi, everyone, and welcome to another episode of AI at the Edge, the podcast where we delve into the latest advancements in AI and machine learning and how they are shaping our world. I'm Shastya, your machine learning enthusiast and tech geek straight from Boulder, Colorado.
And I'm Aubrey, your friendly neighborhood biology buff with a fascination for all things wild and natural. While Shastya over here loves her tech, my heart belongs to the great outdoors and understanding the intricacies of life itself.
Oh, totally. Today we've got something super exciting for you. We're diving into a revolutionary paper titled VpROM, a novel variational autoencoder boosted reduced order model for nonlinear systems by Thomas Simpson, Konstantinos Vlachas, Anthony Garland, Nikolaos Dervilis, and Eleni Chatsi. Trust me, this is a game changer in the realm of reduced order models, ROMs. I know it sounds a bit jargony, but that's why we're here to break it down for you.
Right. And while my expertise is more on how AI helps in conservation and biology, I'm genuinely curious about how it can enhance modeling and engineering. Can you imagine a world where we can predict complex structures' behaviors quickly and efficiently?
It's not just a dream anymore, Aubrey. So let's rewind a bit. Reduced order models, or ROMs, are essential tools used in engineering to simplify complex systems and reduce computational load. They come in handy when dealing with vast systems where calculating everything in real time isn't feasible. Think big constructions like bridges, buildings, and even wind turbines.
I get that. But what makes VpROM so special compared to traditional ROMs?
Great question. Traditional ROMs often use methods like proper orthogonal decomposition, POD, which work well for linear systems but hit a wall with nonlinear systems. Imagine trying to map the rugged terrain of the Rockies with a straight-edged ruler. It's impractical, to say the least. To get around this, engineers would create multiple local ROMs to handle various scenarios, but it's cumbersome and computationally demanding.
That sounds like a messy workaround.
Exactly. This is where VpROM steps in as a savior. VpROM uses variational autoencoders, VAEs, which are types of generative models to create a more flexible and precise reduced order model for nonlinear systems. Essentially, it replaces those cumbersome multiple local ROMs with a more dynamic and unified approach.
Okay, slow down a bit. How do these VAEs actually work in this context?
Picture a VAE as an artist who looks at a landscape and creates a simplified yet recognizable painting. This artist doesn't just copy, but learns the essence and can reimagine it. A VAE essentially learns a lower dimensional representation, latent space of the complex data, and uses this to generate accurate approximations. When applied to ROMs, VAEs estimate the matrix of coefficients that define the relationship between parameters and the system's behavior, allowing for high precision even with nonlinear attributes.
Ah, that's cool. So in the paper, how exactly did they show VpROM's effectiveness?
The authors tested VpROM on some pretty challenging benchmarks, including a wind turbine model and an earthquake simulation. In both cases, VpROM outperformed traditional methods by significantly reducing errors and computational time.
Wind turbines, you say? Now you've got my attention.
Yep. For wind turbines, the models often have to run simulations that consider nonlinear material behavior, which is complex and varies with different conditions. VpROM tackled this problem adeptly by generating reduced models that still captured the physical relevance and robustness required.
And I assume this means faster and more efficient calculations?
Absolutely. With VpROM, they observed almost a 40-fold increase in computational efficiency during the evaluations. That's not just a marginal improvement, it's transformative, especially for real-time applications like digital twins or predictive maintenance and structural engineering.
Amazing. I can see why this would be a big deal. But what about uncertainty? We biologists have to deal with a lot of unpredictable variables. How does VpROM handle that?
Another spot-on question, Aubrey. One beauty of using VAEs is their probabilistic nature, which naturally lends itself to uncertainty quantification. VpROM doesn't just spit out numbers. It provides a range, a confidence interval, if you will, on its predictions. This additional layer means engineers can gauge the reliability of their models and make more informed decisions.
You know, I came into this episode with some skepticism, but now I can see the immense potential here. It sounds like VpROM is pushing the boundaries of what's possible with ROMs in engineering.
That's the idea. And the potential applications are massive. From real-time monitoring of structures to advanced simulations for predictive maintenance, VpROM could reshape how we approach engineering problems.
This all seems almost too good to be true. Were there any limitations noted in the paper?
Well, no technology is perfect. One significant challenge with VpROM and VAE-based approaches in general is the complexity of the training process. It requires careful tuning of hyperparameters to get the best performance. But the benefits far outweigh this obstacle.
So it's like preparing a gourmet meal, a lot of prep time, but oh, so worth it.
Exactly. And with advancements in AI and machine learning, who knows, the training process might become more streamlined in the future.
Fascinating stuff, Shastya. Each time we do one of these episodes, I'm more convinced that AI will change the world, and hopefully for the better.
I have no doubt about that. Well, listeners, we hope you enjoyed this deep dive into the world of VpROM and how AI is revolutionizing engineering simulations. Thanks for tuning in to AI at the Edge.
Yes, thank you, everyone. And remember, whether you're scaling a mountain or crunching numbers, keep exploring and asking questions. See you next time.
Until then, stay curious and keep pushing the boundaries of what's possible. Goodbye.
Microphones on, we're ready to go. Talking about AI, don't you know? Neural networks and deep learning too. In this podcast, we'll break it down for you. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data science models, we can't get enough. This podcast rocks, it's never too tough. Questions, we've got the scoop. Join our tech-savvy podcast group. From beginners to pros, come one, come all. Machine learning's fun, we're having a ball. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data science models, we can't get enough. This podcast rocks, it's never too tough. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data sets models, we can't get enough. This podcast rocks, it's never too tough.